We shall start with an introduction to network namespaces in Linux. Network namespaces in Linux allow for multiple isolated networking environments to run on a single Linux host. Each network namespace is isolated. Now, each network namespace has its own interfaces and networking stack. Processes can be dedicated to any one of the namespaces, and they will see the networking stack of that network space only. To connect network namespaces, we use a virtual network device pair that provides an abstraction or a tunnel between two network namespaces, and they can be used to create a bridge between network devices. Now, we have seen this veth devices being created by Docker earlier. Docker also uses network namespaces to provide isolation to its containers. So each container will have its own namespace that will have its own devices. So by default there is a root namespace, and all the devices on the host would by default appear inside the root namespace. But we can add namespaces as well. So what we can do is, for example, if we look at this diagram, we have here two namespaces, and then there is like a veth pair. This is what the veth pair is referring to. It's like a cable really with two ends, each connecting to one namespace. Now we could even connect this, for example, scrolling down to this diagram. We can even connect this to a switch. For example, here they have used Open vSwitch. However, this can be a bridge as well. So we shall move to Open vSwitch, but before that we shall look at a simple example of creating namespaces and connecting them through a bridge device that we already have on our machine. Now, as we know the devices, let us check it once. So the devices on the host, as we know, the VIR-BR1 that we had created, this was created using Virt Manager. We have Docker 0 bridge that was created by default by Docker. Then we added another bridge. We created another network in Docker. Let us see Docker network ls. We had used this DNet. We created this Docker network to host the application that we had developed in the last session. So this is referring to this bridge device. So we have a couple of bridges already here, as we can see in this diagram. All of them are currently down. We have three bridges, that is VIR-BR1, a Docker 0 bridge, and the DNet bridge. So what we can do is create network spaces and then connect these network namespaces using any one of this bridge. So let's see how we can do that. Let us create two network spaces, one red and the other one, let's say, blue. So here I shall enter the red terminal, let's say, the red namespace. So exec inside red, that would be bash, and we require sudo access for that. So we are now inside the red network namespace. To indicate that, let us make this as a red background, and the same thing here we shall enter the blue namespace. So we are now inside the blue namespace. Let us make it as a blue background. So if I check the IP addresses here, or the devices here, we see that there is only one device, loopback device, and there is nothing else. And here as well, there would be only one device, that is a loopback device. Both of these are down. So we can check that in our network diagram as well. So let us see net show. It is really not appearing here. They only have loopback, but we can see that in our full diagram. So let us see all these namespaces and network devices here. We see a lot of other namespaces, the other applications that are running. However, we are only interested in this one, the blue and the red, which only have loopback devices, both of which are down. Then we shall see how to connect them to our other devices. These are the physical devices, but we shall use the virtual devices to connect them. So now we have network namespaces. Let us add the virtual Ethernet pairs so that we can connect these two namespaces. So virtual Ethernet we shall first add on our root namespace. So for that we shall use this command IP-link add. Now I need to specify a name. Let us say that interface name would be ETHR for red namespace. The type would be veth, and a peer name, that is the other end of this link, that let us call it veth_r. So eth_r, this end would be connected to our namespace. veth_r would be connected to the bridge that is inside the root namespace. The bridge doesn't appear inside any of the namespaces, it is inside the root namespace. So let us create this pair. We'll require sudo access. The pair is there, it is created. We can check that using our IPA command as well. So now we see that this veth_r and this eth_r are created here. Its peer is veth_r and veth_r's peer is eth_r, as we can see. So now that we have these two pairs, this pair, we can attach this eth_r to our namespace and this veth_r to our bridge. Now to do that, we shall use this command. Now this is the command IP-link set, then eth_r, that is our for the red namespace, and then I'm going to put it inside the network namespace red. It requires sudo, of course. So it is now inside the red namespace. Now if we check the IP here again, we see that that pair is no longer appearing here. It is no longer inside the root namespace. Only the veth_r is inside here. And this veth_r has to be inside the root because we need to connect it to either one of a Docker or VIR BR1 or this one. So we can check on our red namespace here. We see this eth_r is now appearing here. It is now inside the red namespace. Similarly, we'll create another pair and put one end of that inside the blue namespace. So repeat the same process here. So we used this command. We shall use this command again. But instead of R, I am going to use B for blue namespace. I'm sorry, we didn't create it. We need to first create the vth pair. We didn't create the blue one. So let us first create the blue. So this would be the command eth_blue and eth_b and veth_b. So new pair created. Now we could move it to the blue namespace. Yes, it has been moved. The other pair should still be inside this. Let us check that. Yeah, the other pair, the other end, veth_b is still inside the root namespace, and the eth_b should appear here. Yes, eth_b is appearing here. So eth_b is now inside the blue namespace. So now let us check our diagram again. So now we can see this in this diagram. We have this red namespace, eth_r inside that namespace, and eth_b inside the blue namespace, and they have their peer. Now all we need to do now is connect this veth_b to one of this bridge, both veth_r and veth_b to any of this bridge for these namespaces to talk to each other. Now these namespaces won't be able to talk to each other without that because they are isolated. we shall connect both of these veth pairs to this Docker 0 bridge. To do that, all we need to do is set the master of that pair, of that veth port, as the bridge device. So for that, what we need to do is use this command. So what it will do is simply set the link, that is in our case veth-r or veth-b, to our master. That would be bridge. Let's say it's Docker 0, sudo this. It has been set. Let us do it for the other one as well, that is veth-b. Yeah, so now it is connected. It should be connected. Let us check our net diagram again. Yes, so now we see that what's happened here is now veth-r connecting to this Docker 0 bridge and veth-b also connecting to this bridge, and they have their own namespace. So now we have this. What we need to do is bring this up, both this eth-r and eth-b, assign them IP addresses, and then bring the Docker 0 bridge up as well, so that both these namespaces can then talk to each other. So let us do that. So first we need to assign IP addresses and bring them up. We'll do that in both the namespaces here. So let us first assign an IP address using the IPA command, of course. Now to connect to Docker bridge 0, as we see it has 172.17. So that network range and that network address we had to use. So that would be 172.16 and 17, and the network ID would be 16. So let us say assign an IP address of let's say 51 to this. We'll assign 52 to the blue one. So 51 by 16, and then device would be ETHR. Right, this will add an IP address there, and the link also we need to bring it up. IP link set on device ETHR up. So let's do the same thing over here. I'm going to copy this one as it is. I'm going to paste it here and change the names appropriately. Assign it IP address of 52, let's say. And then also set this as up. We would check the IP addresses here. The IP address has been assigned. Now the loopback is also down, so we can bring up the loopback as well here. We want to set the loopback. Yeah, so now I think we are ready. The loopback is up as well. Yeah, now they have the IP addresses. So let us check on our host. What's the status? Yeah, we see these are still down. We still need to bring these up as well. So let's do that now. veth-r and veth-b. So that would be sudo IP link set. So I will say veth-b and veth-r. So let us do veth-r first. Set it as up. Set the b as up as well. We have this blue namespace with 52. We have the R red namespace with 51. Both of them connecting to the Docker bridge. So that means now they should be able to talk to each other. Let's check that one. Let's see, we'll ping the other one from here. This has an IP address. This one, copy this, paste it here. It is able to ping as expected. So ping the other one from here as well. It is also able to ping. So now they are able to ping. So what happens if we now let's say bring the Docker bridge down? IP link set Docker 0 down. We need sudo for this. It is down now. Let us see, the ping would have stopped. It is not stopped here because by mistake I'm pinging the same machine here. So this is the IP address of the same machine. Let us ping the other one. That would be 51 really. Yeah, it's not able to ping. Here as well you can see the destination host is really not reachable. So let us try to bring that bridge up again. Make it up. Yes, we see that the ping immediately resumes. So in that way we have seen now how to connect different namespaces via a bridge. Now like that we can create as many namespaces as we want. Docker also creates namespaces like this. So what we'll do is now if we try to bring up a Docker container, that should by default connect to this bridge, and they should be able to talk to both of these network namespaces. So let's try to do that. So I'm going to launch the same busybox image that we had used earlier. So run the busybox image. I shall also use the rm command. Let's simply call it mybox. So I've already specified the rm. Alright, by default it will connect to the Docker container, Docker 0 bridge. It's running now. Let's check the IP address here. So it has an IP address of .2. Now let us also check our net diagram. Yes. So as you can see here, this eth0, this one is really that Docker container, the busybox image. It has its own namespace. It also has its own veth pair. As you can see, this was created by Docker. So that is what Docker does behind the scene. It simply creates a namespace and then creates a pair, veth pair, that it uses to connect to this. So now from these namespaces we should be able to ping our Docker container. Let's see if we could do that or not. Stop this ping. Instead ping 2, that is the IP address of our container. It is able to ping as expected. Now since our bridge 0, Docker 0, it has a network translation NAT, it should also be able to ping the internet. Let us see if the blue namespace could ping internet. It's not. We know why it is not working, because the route is not there. So if we try to add the route, then it will be able to ping that. So we see no route. So let's add a route. Right, this is the one. So now let us ping this. So now it is able to ping. Now however we didn't add it here, so this namespace should still not be able to ping 8. Right, it's not reachable. However, we can add the route, then it should be able to ping the internet. So to summarize, what we have done is created 2 namespaces, connected them to a bridge via a veth pair, similar to what Docker does with its containers. So now let's move on to the next part. Now we shall move on to Open vSwitch. First we need to install the Open vSwitch packages. Open vSwitch packages are available on the internet. You can go to the official website here and download the package for your operating system. So what I'm going to do is now install Open vSwitch. We could either install from source or we could install from pre-built packages that are available. So luckily we have some packages for Debian, the Ubuntu system that I'm running. So we have apt. We will use these two packages, the Open vSwitch switch and common. These are the basic packages required. They have listed some other packages as well, but for now we will only require these two packages. So let us first search on apt. Right, we see a couple of packages here. We would like to get this one, and we would like to get this Open vSwitch. We would also install Python 3 Open vSwitch, which provides Python 3 bindings. So let us install these three packages. The packages are downloading and they will be installed shortly. Right, the installation is finished. To verify the OVS installation, we can use this command OVS vsctl, then -- version. We see that the version is 2.17.9 and the DB schema version is 8.3. This indicates that the installation was successful. Now that we have installed OVS, we shall go ahead and create virtual switches and then connect Docker containers, virtual machines and network namespaces to that switch. So let's get started with that. Currently we have no OVS switches, so I can add a switch. I can use this command add br. So add br and then the name of the bridge. So I'm going to add OVS br1. So we can check on our network diagram here. The OVS br1 is appearing. It is a switch. We can also issue the show command to see the bridge appearing here. Now we shall connect a network namespace to our OVS vSwitch. So for that, first we need a namespace. Let us create one namespace called myNS. We can connect this namespace to our bridge via a veth pair. So let us create a veth pair first. So a veth pair with ethx and vethx. The pair has been created. Now we need to move one end, that is ethx, to our network namespace. So we shall use this command link set. Right, the pair has been the end has been moved to the network namespace. Now the other end we shall add to the OVS bridge, that is our OVS br1, using the add port command. The vethx end has been added to our bridge. Let us see in this figure, we see the MyNS network namespace connecting to the bridge via our ethics, vEthics, that is the veth pair. Now I shall assign an IP address to this virtual bridge, that is our OVS, so that it acts as a gateway. So the IP address of 192.168.0.1 was assigned to the bridge. That is the IP address of the switch itself. So now I shall assign an IP address to our network namespace. Let us move to the network namespace, then check the IP address here. We see that the eth_x is appearing here. We need to assign an IP address here. So let us add an IP address of .10. And also bring the link up. We can also add a default gateway here. Let us check the routes. We see no default route, so we can add a default route via our OVS bridge. So the route was added. Now let us see the IP address of .10 has been assigned to this interface. So that means it is now connected. But we need to bring the OVS BR up as well, the OVS switch itself. So use this command and also bring the veth_x pair, that end, up as well. So let us see our diagram. Now we see everything is up. We have the IP address assigned to the bridge and the network namespace as well. So now they are connected. So let us try to run a DHCP server here. This DHCP server will run inside the namespace MyNS, and it will be used to assign IP addresses to any other entities that connect to our OVS BR1. So I'm going to copy this and run it inside the network namespace MyNS. Right, the DNS mask or the DHCP server is started. It is assigning IP addresses within this range. So now if we connect let's say a virtual machine to this bridge, then it should be able to get IP address from the DHCP server that is running in the MyNS namespace. So to connect a virtual machine to the switch, we need to first create a virtual machine and then assign an appropriate network type to that. So let us start the Vert manager. Now I have one Debian 12 image here, that is a mini OS. It is a live operating system. So we can see this network, it is already connecting to our Docker 0 bridge. So I need to change this to our OVS switch, which is OVS BR1. So the other bridges are not required at the moment, and we can filter them out later. Let us change this to the OVS BR1. Click on apply, and also we need to change this type. We need to provide a virtual port type as Open vSwitch. Click on apply. The changes have been made. Now we shall start the virtual machine. The virtual machine has started. It is showing the desktop. Let us see in our diagram. We can see it is using this TAN port, that is VNet1. Let us filter out the other virtual devices that are not being used. So now we see the OVS BR1 that is connecting to both my network, MyNS and VNet, the virtual machine. So let us check the IP address here. It must have obtained an IP address from the DHCP server that was running in MyNS network namespace. So we can see this IP address 192.168.0.168 has been assigned to this virtual machine. Let us ping the other network namespace to check the connectivity. I shall first ping the OVS bridge itself. It is able to ping. Now I shall also try to ping the network namespace where our DHCP server was running. That was at an IP address of .10. The IP address is 10 here. We need to ping that IP address. It is able to ping. That means it has connectivity. So now our VM and namespace are connected via the OVS BR1. We can also add Docker containers. We can connect containers to this OVS BR as well. So to do that, we shall first run a container. Let us start this busybox container again, but the network shall be none. It shall not be connected to any network. We shall later on add the interfaces. So start the container. We are now inside it. Let's check the IP. There is only one loopback device. Now we can use this OVS docker command to add a port to a Docker container that will connect to one of the OVS bridges or the switch. So let us use this command. So we shall use this OVS docker command to connect this eth_d inside the Docker, that interface to our OVS BR1, the container name specified by my box. The IP address is also specified as 50. So let us use this command. So the port has been added and the Docker container is now connected to our OVS BR1. Yes, we see this PIDSH, that is eth_d, being used by the Docker container to connect to our OVS BR. We can check the IP address here as well. We see this eth_d device appearing with the following IP address. Let us try to ping the other, let's say, the network namespace. It is able to ping the network namespace. It is able to ping the 168, that is our virtual machine. So now the network namespace, the virtual machine and our Docker container all are connected through the OVS BR1, that is a simple level 2 switch. Now like that we can add as many virtual switches as we want using the add br command. So now what I'll do is try to create another virtual switch, a second virtual switch. We can see the second bridge is added. Check on our net diagram again. We can see this bridge is appearing here as well. So now I will connect another namespace here called CLNS, that is for client namespace. It is just to mimic a host that is connected to the second bridge. We shall use this vth pair again to connect our client namespace to the second bridge. Now move the pairs appropriately, one end to the network namespace, the other end to the second bridge. Also assign an IP address to our second bridge. Let us assign IP address of .2. Now we need to bring this bridge up. Let us bring the bridge up as well as the VHC interface. Now I shall move inside the client namespace and set the links up there as well. So we are now inside client namespace. We check the devices here. You see HC here. We need to bring this up, but we shall not assign an IP address here. We shall use DHCP to get an IP address. The DHCP server, as we know, is already running, but it is connected to the first bridge, not the second one. So we shall now connect these two switches together. We can see this client namespace connecting to the second bridge, and we shall use the DHCP server running in MyNS to get an IP address for our client namespace. So for that we need to connect both of these switches via a patch link. So for that we first need to add a port to our OVS BR1. Let us add a port here called P1 on OVS BR1. So we can ignore this error for now. There is an error setting up, however this port was already created. The second port is also created. We can check this in our diagram. This P1 and P2 appearing here. So now we shall configure these ports as patch types, where the peer for P1 is P2 and similarly the peer for P2 would be P1. Right, now let us see our diagram again. We can see that these two are connected, however it is not clearly visible. The lines are merged. Yes, now it is a little bit more clear. We can see this P1 and P2 are now connecting these both switches, that is OVS BR1 and OVS BR2. So now this client namespace should be able to get an IP address. Let us see. So we can run this DH client on our HC interface to get an IP address. Let us run this command. Yes, the command is completed. So let us see if we got an IP address. So we obtained an IP address of .169 on our client namespace. Let us check it here. So now we can see both of these a little bit clearer. The client namespace also has an IP address assigned to it, which was assigned by the DHCP server running on my network namespace. Now both these network namespaces are connected to their respective switches, which are in turn connected via the patch port. So with that, let us first try to ping the network namespace. Yes, we are able to ping the network namespace from our client namespace. So let us also try to ping the other virtual machine and the containers. Let us ping container. We are able to connect to the container. Let us also try to ping the virtual machine, that is at 168. So we have connectivity with the VM as well. So now both of these are having connectivity to our client namespace, and our client namespace also got an IP address. So let us also try to ping the other way. We see that the Docker container is also able to ping. So with that, let us conclude this demo. In this demo, what we have done is created virtual switches and then added network namespace, connected network namespaces, virtual machines and containers. We also connected two Open vSwitches via patch ports, the patch cables. In the previous demo, we had created some Open vSwitches. These switches support the open flow protocol. Let us check the flow entries on these switches. We see a single flow entry on the first Open vSwitch, that is OVS-BR1. It has an action set as normal. This entry is present by default on an Open vSwitch, and this makes it behaves like a layer 2 switch. However, in case of SDNs, we would like to modify these flow entries dynamically with the help of something called an SDN controller. So we shall now look at an example of using an SDN controller, and for that we shall use Mininet. Mininet is a network emulator. It can help us to emulate large and complex networks to test our SDN controllers. We can download Mininet from the internet. There are multiple options. Either we can download a VM that has Mininet installed in it. We could also build from source, or we could install from package. We have a Mininet package for Ubuntu system that I'm running. So we will install this package using apt. Right, the package has been installed. Now let us check. Yes, the version is showing correctly. That means it's installed correctly. Now one more thing that we need to do is clone this official Mininet repository from the GitHub. It has some additional tools that would be useful. I shall clone this repository using the git clone command. Right, the repository has been cloned. Let us cd into it. Now I shall install this repository since it has a setup file. We can use pip to install it locally with the -e option. So it will install the Mininet module on our Python installation so that we can use that Mininet. And that would be useful for MiniEdit. That is another program which provides a GUI for our Mininet to create the topologies. Run this. So this would show up this GUI. Now here we could create topologies such as we can add hosts. So we can add multiple hosts like this, and then we can connect them using say some switches such as an open switch, a legacy switch that is not OpenFlow capable, and legacy routers as well. We can connect them using links like so. Now here only the OpenFlow capable switches, which are the Open vSwitches, we can only connect these controllers to the Open vSwitches. We cannot connect them, for example, to this switch that is a legacy switch. It does not support OpenFlow. So like that we can create various topologies, and then we can use this topology to test our SDN controllers. Now we shall look at Ryu SDN controller. Ryu SDN controller is available on GitHub. You can go to this repository and download the source code. Now Ryu controller is not being maintained currently. However, it is a good point to start. It is fully written in Python and supports Python 3 as well. So we shall clone this repository. We can use this command Ryu Manager and then launch our app, which is a Python file. So this app would be our SDN controller. We have some optional requirement as well and some prerequisites. I shall first install these prerequisites on my Ubuntu system. Alright, now we have the prerequisites. I will clone this repository. Right, the repository has been cloned. Now we can cd into this folder. Now we shall look at an example of building an SDN controller using Ryu. On the official website, we can go to the documentation section and find this book. This is a comprehensive guide to Ryu controller using OpenFlow 1.3. The PDF version is available. One can get this book. There are various examples. The first example here is a simple switch application which is implemented using Python. They have provided this implementation in the switch 13 Python script. The full implementation is given here as well, and that script file is also available on the Ryu repository. We can check the Ryu repository we had cloned earlier. Under the app folder, we see this switch 13 script, which is a controller. We can use this controller as a template to write our own controller. We can see that this script contains a single class that inherits from the Ryu app. Now this is our controller class. Now Ryu Manager, it follows a event-based programming paradigm where we have our application, the controller, running a loop which handles all the events that are created by the switch. Now the first thing we need to do is add a table flow or table miss flow entry, which indicates a default entry if none of the packets match any of the other rules. If the packets don't match any rule, then this rule will be applied and it will be pushed to the switch by config dispatcher. We see that this function is here. In this function, there is a single match being created, which is an empty match that matches all the packets, and then the actions are set to as forwarding that packet to the controller. So if there is a packet which doesn't match any other rules, it will match this one and it will be forwarded to the controller. We can see that the priority of this rule or this flow is 0. That means it has the lowest priority. That means it will be matched at the end. Now coming to packet in message, we have a packet in event handler that uses main dispatcher. There are various fields here. The first is a match, that is the match rule that was used to handle this one.
is to match this packet. We have data and total length of the packet and the buffer ID. So in the code we can see that this is that function packet in handler that will handle these packet in events. So what it is doing is extracting some information from the packet itself. It gets the data path, that is the switch. It gets the port. Then we can create a packet class. It also extracts the Ethernet header information from which we can get this destination and source MAC addresses. And what a level 2 switch will do is store this MAC addresses and have a table, a MAC to port table, where it will store this. So it will learn which port is mapping to which MAC address. So that will be handled and stored in this dictionary. So that is being added at this line. We see the data path ID and the source. We will set the port as import, and then we shall use that to forward the port or to decide the output port. So if the destination is there, we would have stored its ID already, or the port, and we shall set that port as the output. But if there is no such port, or the port hasn't been mapped, then it will simply flood it. That means it will broadcast it to all the output ports. So based on this output port, we build an action that is to just forward this to the output port. And now this is where we add the match rule. So only if output port is not the flood port, that is when it is not broadcasting, only then we will add this create and add this match rule, which is just to match the Ethernet source and destination. It says if there's a packet from import with this destination and this source, then it will match this rule. And once it matches this rule, we can add this with the action, that is to forward it to the output. Now we can add this match or this flow with a priority of 1, because it should be matched before the table miss. And finally what we will do is create a output packet or the output message using the packet out class, and then send that to the data path, that is our switch. So with this application we will have a simple L2 forwarding. We can run this application using the reu manager command. So I'll copy this file, this example switch, to a new file. Right, we have this ctrl.py. Now this is our controller. We could modify it if we wanted to. Now I shall start this controller using the reu manager command. Right, the controller has started, and it is running on port 6633. So currently it's not outputting anything because we don't have any open switch. We don't have a topology. We need to make a topology and an open vSwitch, which will receive commands from this reu controller. So we can use mini edit to create a simple topology. I shall add a few hosts here and a switch and a controller. Now we can save this topology as an MN file and also export it as a Python script which we can directly run. So one thing I forgot was to assign the controllers. So the controller here must be assigned as a remote controller because it will be running using the RU manager on that port. So now I can save it again. Export the script as well. Right, now we can start this topology. Simply run the script that we had exported. Right, the topology has started and we can see some log messages appearing on our RU controller. So this is the negotiation or the handshake that's happening between the controller and the switch. We can see that Pininet in fact creates this open vSwitches. We have this bridge S1 and the ports there for our all the 4 hosts that we had connected there. Now we can also check the flow entries on the switch. So during negotiation, one flow entry, that is table miss, must have been created there. So let us check that. I shall open this in a new terminal. Run it here again. So this is that one entry, the action specified as forwarding to controller, the table miss entry. If we try to, let's say, ping this host, then the other flows would also be added. Let's say H1 ping H2. Now we can check the flows again. We see 2 additional flows have been added. That says forward from H2 to H1. So if the packet comes from H2 with this source and this destination, then output should be to the other port. And similarly for H1, the output should be H2. So if we try to ping the other way, let's say H1 ping H3, then the other flow entries would also be added between H1 and H3. These additional 2 entries are now appearing here. You can check the flow entries here again. These are all the possible flow entries in our level 2 switch. All the priorities are set as 1, which would be matched before the table miss entry. So that was a simple layer 2 switch. For more information on this functions and classes, one can refer this documentation. There are other examples here as well, such as this traffic monitoring application and many other applications here. So we will recommend one should check this documentation for full treatment of these example applications. With that, I shall end this demo. Thank you.